we're going to start with a regular hexagon who has the area of root 3. Now, on the upper side of the hexagon, we're going to put a parabola so that it touches the upper three vertices of our hexagon, and we're also going to put another parabola on the bottom who's going to follow the same rules, so it will touch the bottom three vertices of our regular hexagon, as you can see on the sketch. The question is, can we somehow calculate this shaded red area? This problem was presented to me by one of my subscribers, Mary, from Toronto. She says that the similar problem was on a math competition in her country and that she couldn't work it out. So don't worry, Mary, we're going to get to the solution. Of course, if you guys want to try this one out for yourself, you can pause the video as always and then come back and check the solution. Alright, so let's solve this one. So I'm going to start with our regular hexagon. We know that the area of the hexagon is equal to 6 times the side square times square root of 3 over 4, and we know that our area is equal to square root of 3, so we can find the side of our hexagon. Of course, just as a quick reminder, this formula for the hexagon is due to the fact that the hexagon consists out of 6 identical equilateral triangles. So let's find the side of the hexagon by first simplifying the square root of 3, and we will get the following. This is of course 2 over 3, which means that the side is equal to square root of 2 over square root of 3. Of course, we can rationalize this and get that the side of our hexagon and also at the same time the side of one of our equilateral triangles is equal to square root of 6 over 3. Now, in order to find our parabolas, we will use the analytical geometry because this will be the easiest way. So, first I will have to find the equation of the parabola, but first I will have to place the coordinate system, and I will do it in such a way so that coordinate beginning is located at the center of our hexagon, as you can see on the sketch. This is going to be super useful because now we can concentrate on the top parabola. Let's try to find the equation of this parabola, or to be more precise, the vertex form. This form in analytical geometry looks something like this, where coefficient A actually represents the direction of a parabola, so it will tell us if this parabola is facing upward or downward, and it also represents the width. So, since our parabola is facing downward, we will probably expect A to be a negative value. Now, H and K actually represent the coordinates of the vertex of a parabola, as you can see on the sketch. Now, in order to find this, let's go back to our hexagon. You can see that the vertex of our parabola is located at the top of our hexagon, and it is located on the y-axis. This means that the coordinate h must be equal to 0, and the coordinate k will be equal to the one side of our equilateral triangle inside the hexagon, so it will have the value of square root of 6 over 3. Now we know the values of h and k. And in order to find the value of A, we need at least one more point on our parabola. And we're going to use the point on the right side where the parabola touches the hexagon. We can easily find the coordinates of this point if we notice one of our equilateral triangles. You can see that the x-coordinate of this point is nothing but the height of our equilateral triangle, and the y is actually equal to the half of the side of our triangle, so we can easily calculate those values. Let's start with the x. This is equal to the side square root of 3 over 2, since this is the formula for the height of equilateral triangle. We will substitute s for the value of our side, and we will get that this is equal to square root of 2 over 2. Now, If we do the same for the y and substitute the value of the side, we will get that y coordinate is equal to square root of 6 over 6. And those are the x and y coordinates of our point. Now, those are exactly the x and y coordinates which we need to implement into the formula for our parabola. If we do this, we will get the following equation. Now, we can simplify this by first squaring everything inside the brackets. Then, we can simplify some more by multiplying everything with 6 and get rid of the fractions. And finally, when we work through this, we will get that a is equal to negative square root of 6 over 3. And as you can see, we got the negative value of coefficient a, which actually corresponds to our parabola, which is facing downward. Now, let's substitute the values of h, k, and a back into our original equation, and we will get the following equation of our parabola. Now, we first need to find the area in between our two parabolas. And we're going to do this by simplifying our task. First, you will notice that this area actually has two lines of symmetry, x and y axis. So we can basically calculate 1/4 of this area, the area inside the first quadrant, and then we can multiply this with 4 to get the overall area in between those two parabolas. So this is the idea. But how do we do this? Well, the simplest way is to use a definite integral. And to get this integral, we need two things. The first one is the equation of the parabola, which we already have, and the second one is two values for the bounds of our integral. Those two bounds will actually be two x coordinates of the points which are bounding our red area from the sketch. You can see that we already got the first bound, which is equal to 0, so this means that we only need to calculate the x-coordinate of this other boundary point. We can do this easily by noticing that this point is located on the x-axis, which means that the y-coordinate must be equal to 0. Now we can substitute the value of y, or 0, inside the equation of our parabola and work through this to get the value of x. We will first simplify our equation by multiplying everything with 3 over square root of 6, and we will get that x squared is equal to 1, which means that x must have the value of plus and minus 1. This is also correct because, if you remember, our parabola is crossing the x-axis in 2 points, first one on the right side, which will obviously have the positive value of plus 1, and the other one is on the left, which will have the value of negative 1. Of course, we're just going to use the one on the right, and now we have everything that we need for our integral. So our red area, which is 1/4 of the overall area, will be equal to the integral, which has the bounds of 0 and 1, and of course we are using the equation of our parabola. Now let's work through this integral. First, I'm going to isolate the minus square root of 6 over 3, since this is the common factor, and it is a constant value, so it will not affect the integral. And then we will separate our two values inside the integral so that we will form two individual integrals, as you can see here. Now, the solution for those two integrals is really simple. For the first one is x to the power of 3 over 3, and for the second integral, it is x. So both of them will have the boundaries from 0 to 1. But due to the fact that the lower boundary is 0 and it will do nothing in this particular case, we will just substitute the value of 1 instead of x and get the following. Now we're going to work through this by finding the common denominator inside the brackets, simplify, and we will get that this integral has the value of 2 square root of 6 over 9. Now, of course, we want to calculate the whole area, which is equal to the 4 times the area of this segment which we calculated. So we can substitute our value and get that this red area is equal to 8 square root of 6 over 9. Now let's put our regular hexagon back into the story, and if we do that, we can easily see that the red area actually represents the difference between our full area and the area of our hexagon. So we're going to substitute those values, and if you want to, we can get a little bit fancy by finding the common denominator and put square root of 3 as a common factor and get our solution. Of course, you can leave it in this form, or if you like approximations, the numerator of this fraction actually really nicely approximates to 4, so our area is basically 4 over 9. But if you don't like the approximation, you can of course use the previous value, and those are our solutions. Well, I hope you guys enjoyed this interesting problem. If you did, do not hesitate to leave a like and consider subscribing to the channel. Those stuff really means a lot. Of course, if you found another way to solve this problem, please write it down in the comment section. I always love to see you guys finding different solutions for the same problem. And again, as always, until next time, see you all, take care.